It's great. Yeah, I think now it's work. So are you ready?
Yeah, I'm ready. Yeah.
Sorry for the delay. Let's start today's seminar. Today's speaker is Dr. Jaehoon Jeong from KIAS, and he's going to talk about the Anapole dark matter in all scenarios. Please go ahead.
Thank you. Thanks for the invitation, and then I'm really excited to be invited to this Sogang National University because when I was a high school student, the Sogang National University has a high level cutoff. So I finally failed to come to Sogang University, but after became a postdoc coming to here, I'm really happy. And then this is the first time to give a talk after the invitation. So today I'm going to talk about kind of the dark matter scenario, which is the hypercharge Anapole dark matter about all the spin scenarios. Here, the all the spin means the Anapole dark matter particle can have arbitrary spin. And then just 2 days ago, our paper was published. So I delivered my the renewed presentation version, but I think it is not delivered yet well. Anyway, and then this work has been taken in collaboration with Professor Song Choi and Dr. Dong Gwang and Professor So Dong Shin. All of these collaborators are now in Jeonbuk National University. Let me briefly introduce the motivation of the dark matter searching. As you can see, these figures, maybe most of you have seen these figures a lot of times. But in order to make stronger my motivation, I'm going to briefly introduce about the searching for the dark matter. Just going back to this figure, as you can see, there are many practical evidence for implying the presence of dark matter. And because of these evidence, many people started to study many models explaining the dark matter observation in the particle physics point of view. These are the just nothing but list of the beyond the standard model explaining the dark matter observation. Here, what I want to emphasize is that according to the observation, we know that in the universe, the dark matter occupy about 27%. So if we can identify the dark matter, then it would be very crucial to identify the new physics. By the way, as I told, as you saw before, all the observation for the dark matter has a very few information. Up to now, what we know is only the gravitational effect of dark matter. So, because of this few information of the dark matter, we can naturally assume that the dark matter particle is electrically neutral and colorless. Of course, you can consider another scenario. For example, the milli charged dark matter. In that case, even though the dark matter is not electrically neutral, since the charge is very small, we can explain the current dark matter observation. But in our case, we are just assuming the natural conditions about the dark matter. And then, in my personal point of view, since there's very few information about dark matter, in this case, in order to search for something, not only the dark matter, I think it is more powerful to assume as low as possible, just reducing the assumption. So in this script, in our work, we just assumed only two conditions. The first one is that the dark matter particle consists of only a single diurnal particle. Of course, in this case, the particle can be elementary or composite. And then in this talk, I'm going to generalize the term Majorana to include all the self-conjugate particle of any spin. Yeah, because the self-conjugate is longer than Majorana. Yeah. And then the second condition is that we consider only the observed gauge symmetry. Of course, many dark matter models assume another gauge symmetry, but in our case, we just assume only the observed symmetry because it is the only one gauge symmetry we can believe because this is observed. Yeah, so even though we consider only these two conditions, the allowed scenario of the dark matter particle is only one. This is the U1 hypercharged Anapole dark matter particle.
So if the matter particle has some magnetic moment, for instance, a very small magnetic, it's not ruled out. If the dark matter particle has some magnetic moment, for instance, or electric dipole moment, it can couple to the electric to the.
No, yeah, because it will be considered the Majorana particle. Then,
Because of the Majorana.
yeah.
Combining the
Yeah,
two.
yeah. The only allowed the interaction is only Anapole interaction.
Okay, yeah, of course.
Yeah. By the way, the Anapole interaction intrinsically generate the higher dimension effective field theory operators. So because of this fact, we can automatically explain the weak interaction rates of the dark matter particle. And since we are considering the standard model gauge symmetry, so mass range can be naturally assumed to be from GeV to a few TeV scales. And then what about spin value? Usually people consider spin 1/2 or 0 or 1 dark matter scenario because there's a many reasons why they are considered only the low spin value. For example, one reason is you will complete model. Yeah. If the spin value of a particle is larger than 2, then up to now we don't have any UV complete scenario. By the way, as I told you before, we have a very few information of dark matter. And then also, even though there's no UV complete theory about the higher spin case, we can consider the composite particle with higher spin particle. So, in such a speed, if there is a very good mathematical formalism which can consider all the spin scenario, then there is no reason to not analyze the higher spin dark matter scenario. So a few years ago, my advisor Song-Yeol Choi and I developed it on a mathematical formalism to construct the general three-point vortex in terms of arbitrary spin particles. So by utilizing the vortex formalism, we analyzed all the spin cases of the Anapole dark matter particle scenario. In our paper, we considered these three experiments. Maybe most of you know this figure there. So from taking the data of the Planck stellite and Jaehoon experiment and LHC, we obtained the coupling constraints versus the dark matter mass. And then also we additionally considered the conceptual constraints which are the unitarity and perturbativity. So finally, by considering these experiments, we obtained the combined constraint plot. And then finally, to say in conclusion first, we found that the spin larger than 2 scenario is almost excluded fully. This is the main result of our work. Here I arranged the studies including Anapole dark matter. Here, in the case of electromagnetic Anapole dark matter, there are many studies which have been done, and also in the case in the direct detection part, there is one paper written by Professors Koper and Sang. And then, as you can see, in the case of spin 1 electromagnetic Anapole dark matter, the Rayleigh abundance and LH search has not been done. And recently, the authors in this paper, they considered the hypercharge Anapole dark matter particle for only spin 1 over the case. In this case, in this paper, they considered all of these experiments, but their limit is only spin 1 over 2 scenario. But in our case, by using the vortex construction mechanism, we investigated all the hypercharge Anapole dark matter scenario in terms of spin values.
I have a question. So here there are two cases, electromagnetic or hypercharge. So in the case of hypercharge, you just include the possibility that you couple with the Z boson, basically.
Yeah.
So what, in the case of LHC search, is it correct to assume electromagnetic only?
So just the correctness is I don't know. It is up to the research approach. Yeah. Even though we consider electromagnetic Anapole dark matter, we can investigate about the data of LHC and.
So you can just put by hand the coupling to the Z boson equal to 0. This is the.
Yeah. In this case. But as you know, in the direct
And so, and then my question is, in the case of hypercharge, how do you, so what is the assumption?
What is the assumption? Yeah, the difference between electromagnetic interaction and hypercharge case, I'll come to you later in detail. But briefly speaking, just in our case, we are considering the U1 hypercharge gauge version. And in this case, they just considered the only photon exchange.
So it's a symmetry breaking that gives you the coupling.
Yeah, exactly. So even though we consider the hypercharge Anapole dark matter case, if we consider the direct detection, then our result is going up. Exactly. So up to now, I showed you all the material to make our motivation more stronger. So our motivation is like this. We took the generic analytic and numerical analysis simultaneously of the hypercharge Anapole dark matter particle of spin 1 over 2 to 2. But of course, our even though we took the analysis up to spin 2, but by utilizing our formalism, we can continue over the spin 2 value. Yeah, first, here, as I said once more, our hunting target is hypercharge Anapole dark matter particle of any spin. Outline of my talk is as follows. First, let me introduce what is Anapole moment. Yeah. Personally, this is my personal point of view. When I started to study the Anapole moment dark matter, any paper explained what is the Anapole moment more explicitly or in detail. So just personally, I studied and I finally understood what is the Anapole moment, even in the classical electromagnetic level. So maybe even though you cannot understand the remaining parts, if I make you understand these parts, maybe I will be successful. And then I'm going to introduce how to construct the Anapole vertex. Of course, it is kind of a mathematical part. I'm going to briefly introduce, and then I'm going to say only the essence about the construction of the general Anapole vertex. And then the next one is the property of Anapole vertex. This property is very, very important to proceed with the numerical analysis. Maybe you can understand if I go to this part. And then I'm going to compare the difference between hypercharge and electromagnetic induction. And then finally, I'm going to show the constraints of the couplings for the spin 1/2 to spin 2 cases step by step about this experiment. And then additionally, as I told you, I'm going to say, I'm going to add the Naive convertibility bound. And finally, conclude my talk. The Anapole vertex, Anapole moment. Usually in the particle physics, if a violent particle is coupled to a muon gauge boson, then in that case the interaction is called Anapole interaction. The trivial example of the Anapole interaction can be found in the electromagnetic interaction. Maybe all of people learn the, how should I say, multiple expansion about the only static electric field. But in general, if we consider non-static electromagnetic field, then by taking the general multiple expansion, then what we can obtain is these three kinds of moments. Maybe these two electric and magnetic moments are familiar with you, but the toroidal moments are a little bit difficult to understand. And in the case of static electromagnetism, we can observe the toroidal dipole moment. But just in this case, please accept only the fact that if we take the general multiple expansion, then we can obtain the electric, magnetic, and toroidal moment in terms. And here the corresponding Hamiltonian, as you can see, each of the dipole moment coupled to electric field and magnetic field. This is the important point, because in the particle physics point of view, we can expect that kind of T-channel process, just exchanging photon, because this electric field and magnetic field will be replaced by photon diagram. So we can understand this Hamiltonian as if an object have a electric or magnetic or toroidal dipole moment, then we can say the object interacts directly with an external field. Then what is the Anapole moment? Actually, the origin of the term Anapole is coming from the Greek letter ana, denoting without. So in English, we can say without pole. Of course, maybe some of you forgot the definition of the pole in the electromagnetism. The definition of pole in the electromagnetism is that the maximal magnitude of electric or magnetic field. So, for example, if we consider this electric dipole, the maximal magnitude of the electric field is there are 2 points. This is the reason why we call this object as a dipole. Honestly, when I studied about this Anapole moment, at that time I didn't know the definition of pole. Yeah, that's the reason why I'm explaining this now. So, because of this definition, Anapole means there is no electric field and magnetic field. it is related to the Majorana particle in the particle physics point of view, right? Then what is the Anapole moment Hamiltonian in the classical electromagnetism? This is given by the product of the Anapole moment and the current density. Please note that since there is current density, not the electric or magnetic field, we can understand as if the object has only the Anapole moment, we can say the object interacts directly with an external current, not the external field. I come to you what is the difference between the direct interaction between current and external field. So in the solid physics, many people tried to make an object with only an Anapole moment. The Anapole moment can be realized by combining the electric dipole and then toroidal dipole. As I showed before, according to the Maxwell's fourth law, here this is corresponding to the toroidal dipole moment term, and the time derivative of electric field is corresponding to the electric dipole moment. So by combining these two moments, we can realize the Anapole moment object. So this is just nothing but the description in the solid physics of the object with only one Anapole moment. Then let's go to let's extend our understanding to the particle physics. Let me consider this interaction. Here, Fusai particle is a spin 1/2 Dirac particle. In this case, we can write down the general Lagrangian like this. Here, this each term is directly related to the electric monopole and anapole and magnetic dipole and electric dipole term. And then by investigating the vertex of this Lagrangian, we can find the non-relativistic limit Hamiltonian of this term. And if we write down the corresponding term, we can obtain like this. In this case, the dipole terms are replaced by the spin operator. As I mentioned before, the remaining parts are coupling to the external field, not the external currents.
I'm sorry, what is mu? Mu?
Mu is the magnetic dipole moment. Yeah. So, in the particle physics point of view, we can interpret such an interaction as a contact interaction. That means that the particle, the Anapole interaction doesn't occur through the exchange of photon. So if we consider electromagnetic Anapole interaction, then this interaction will generate the contact interaction. So if we replace the particle psi as a Majorana particle, then what we can obtain is only the Anapole interaction term. So up to here, this is the my introduction of the Anapole moment. If you have any question, please ask me, or just after seminar, please ask me. Next is a quite difficult part, because as I told you before, in order to explain this part, I need to explain several mathematical point of view. Anyway, I'm going to start to how to construct the general Anapole properties. In order to do that, let me first touch your annihilation process. Here, K1, K2, and P are the momenta of each particle, and these annihilating two particles are identical to each other. And because of the energy momentum conservation law, we introduced only the combined momenta P and Q, which is given by the summation and subsection of the annihilating particle. And in this annihilation process, the total particle is the U1 gauge boson. Of course, now this gauge boson is a massless particle. So this is virtual particle. Since because of the U1 gauge boson, the corresponding 3-point vortex has to satisfy this U1 gauge invariance condition. And here, since now I'm not limiting the number of spin of annihilating particle, I introduced this combination of various 4-vector indices. If these particles are spin 2, then the alpha will be given by alpha 1 and alpha 2, and beta 1 and beta 2. If we are considering spin 3, then there's a alpha 1, alpha 2, alpha 3, something like that. Yeah, and then since the annihilating two particles are identical to each other, so we need to impose the corresponding condition into the 3-point vortex. This is related to the charge conjugation of the 3-point vortex, but just please accept that such a condition is necessary to be imposed. So by imposing these two conditions into the 3-point vortex, the authors in this paper, at the first time they derived the general Anapole vortex for arbitrary spins.
So how do you parameterize a spin 1/2? So half integer spin.
Yeah.
So if you combine the several, for instance, this alpha, alpha 1, alpha 2, alpha 3, you can construct some tensor of a higher rank.
Yes, exactly.
And so you take the irreducible part and it is the highest spin. Okay. For spin integer.
Yeah.
What about this half integer?
In the case of half integer, just we can use just trivial representation. For spin 3/2, you can use the Larita-Schrödinger representation. Yeah, in the case. So in the sense, yeah. So in the case of a half integer, or for example, if we consider spin 5/2, then there is 2 4-vector indices, and then let me write down.
So you combine 4-vector indices with the representation of spin 1/2, for instance. Or
Yeah, exactly. Yeah.
you just combine the lower spins to make higher spins.
Yeah, exactly. Yeah. Yes. So maybe it looks very early, but in order to include all the general case, we should encounter the 30. Yeah. Yeah. Of course, maybe I cannot explain all the details, and then I cannot make you understand it fully. So as I told you before, my purpose is to deliver to you only the essence of our construction algorithm. Yeah. This is the general Anapole properties for fermion and for boson. And then one of the most important points is that the number of independent terms is given by the 2 times the spin value of the Majorana particle. We can count this number of independent terms very easily, but I'm not going to introduce how to count them. Yeah. But the counting the number of independent terms is essential to construct this general 3-point vortex, because the independent coupling is completely corresponding to the number of independent terms, right? So as I told before, a few years ago, exactly 2022, my advisor Song Choi and I developed an algorithm for the so-called vortex construction mechanism. So by utilizing such a mechanism, we can straightforwardly construct the general Anapole vortex. Of course, in this paper, in the original paper, we showed that all the general 3-point vertex, not only the general anapole vertex, but in order to obtain the general anapole vertex, just by imposing these two conditions to the general 3-point vertex, we can obtain the general anapole vertex. So let me briefly introduce what is the vertex construction mechanism. First, we introduced this normalized momenta, just taking all the kinetic values as a normalized value. It is mathematically beneficial to deal with all the complicated mathematical structure. So this is the reason why we introduced this normalized momenta. Here, P and Q, as I told you, is given by the summation and subtraction of the momentum K1, K2. And then we introduced such a convention. This is the so-called the orthogonal metric tensor, because if we couple this momentum P hat and Q hat to this orthogonal metric tensor, then the value goes to 0. So because of this reason, we named this quantity as the orthogonal metric tensor. And then also contracting this orthogonal metric tensor and the gamma matrix, we obtain the orthogonal gamma matrix. And for simplicity, we introduce such a Bracken notation, which is just nothing but the momentum productive Lipschitz tensor. And we obtain the basic operators. These basic operators is very important, very, very important, because for example, in order to deliver our essence, let me consider the wave function of chi alpha and chi beta are coupled to this S0 alpha beta operator. In this case, only if the helicity of chi beta and chi alpha are 0, this operator gives non-zero amplitude, non-zero value. Yeah. If this chi alpha and chi beta have a different helicity, for example, +1 or -1, this operator generates 0 value. All of these operators plays the same role. So just by combining all of these operators, we can construct the 3-point vertex. And then since, as I told you before, we don't limited the number of index of alpha and beta, we need to consider such a repeated appearance of the basic operators. By the way, if we consider the higher spin wave tensor, then the wave tensors are completely symmetric about the permutation of 4-vector indices. So the symmetricity, because of the symmetricity, we can ignore the order of the index. Here, as you can see, there's alpha 1, alpha 1, beta 1, and for the second S0, there should be alpha 2, beta 2. But we don't need to consider the order of the alpha and beta indices. So we can very simply introduce such a notation, and then we can just consider only the power of the basic operator. So here, all the scale Bracken notation is introduced by this simplest notation. So here, yeah.
So here, chi alpha and chi beta are spinors. I mean, Majorana particle.
Yeah.
So alpha beta are the spinor indices and mu.
No. Not spinor indices, just polarization vector indices.
I mean, even same footing as mu.
Yeah. Just alpha, beta, mu are the 4-vector indices. But if you consider Larita-Schwinger field, then you can write down with the spinor and the 4-vector indices too. Yeah. But in this case, what I write down here is only four vector indices. So if we consider the spin half case, then we should remove all the four vector indices. Yeah, but in the case of B mu, this is the U1 gauge version. So this particle is a spin one. So the particle B has to have a one mu index. Yeah. But in the case of chi and these two chi minor particles, it's not limited to have one four-vector indices. They can have a multitude of four-vector indices.
Depending on the spin of chi.
Sorry?
Depending on the spin of chi.
Yeah, exactly. Yeah.
So these basic operators, so that apart from the details, they are constructed in such a way that they vanish for some particular combinations of helicities or outside helicities.
Yeah, exactly. In this case, these two binary particle helicities. Yeah.
So you check all the possible combinations of incoming helicities.
Yes.
And then you just, these basic operators are different from zero, each of them only for some combination. And so you choose the correct one. This is
Yeah.
really-
Yes, exactly. Yeah. That's my essential point. Yeah. So, by the way, as you can see in this general vertex, we categorize each term by counting the dimensionality of cutoff scale. So, yeah, please focus on the power of this term. If we, in order to focus on only leading order term, we need to consider the lower value, the lowest value of tau. So, just removing all the higher order term, what we can obtain is only these terms for fermion case and for integer case. If we ignore all the higher dimensional term, the number of independent terms is given like this. This is nothing but for fermion, there's only one independent vortex, and for bosonic case, there are two independent cases, regardless of spin value. Yeah, of course, I'll come to you to your familiar expression. This is the Lagrangian. Maybe some of you are more familiar with this Lagrangian. This is the famous Anapole interaction term. And then for the bosonic case, we can write down the corresponding Anapole interaction Lagrangian just from investigation of the three-point vortex. And then also in the same logic, we can write down the higher spin Lagrangian. Here, the reason why we named the coupling as A and B is like this. Just investigating the three-point vortex in the non-relativity limit, and we can obtain the corresponding Hamiltonian in the non-relativity limit. Then, by calculating the non-relativity limit Hamiltonian, we can know that the Hamiltonian relative to the coupling A is given by the dipole type Anapole term. And this is the mode parity operator. On the other hand, if we calculate the non-relativistic Hamiltonian or the coupling B, we can obtain the quadruple type Anapole Hamiltonian. This is the even parity operator. Please note that this formula is not written in the paper. Just this formula, in the case of this formula, I obtained myself just because of my personal curiosity. Maybe I think this operator will be related to the non-relativistic EFT. And then next I'm going to, yeah.
This is suppressed, the velocity suppressed or So if you consider the particles in the limit of zero velocity,
Yeah.
the first term has
Yeah.
a non-zero limit. And the second term probably is proportional to zero.
I think this is maybe in the just by connecting the non-electric EFT formalism, this term will be connected to the V orthogonal. Something like
But these two, no, I'm just wondering,
Yeah.
these two couplings are independent.
Yeah, exactly.
So in principle, you can assume that the particle, so you can say that in general, if both are present, A dominates over B, dominates over B. But if you say for some reason A is zero, you can still have B. So I think it would be possible to see what kind of effective operator comes out. Probably it will be a suppressed, a velocity suppressed operator.
Yeah, exactly. Yes. Oh my God. Yeah, exactly. Yeah. Next, I'm going to say the property of Anapole vertex. In order to do that, first let me consider this annihilation process of two binary particles. Because of the U1 gauge impedance condition, the propagator can be decomposed by the product of two spin-1 polarization pair. And then by imposing the identical particle relation, explaining the imposition of the identical particle relation is pretty difficult. So just I'm going now I'm mentioning only the imposition of the identical particle relation. And finally, in the cross-section level, we can observe that these annihilation part and production parts are completely decomposed by the multiplication. So what we need to consider is only this annihilation process, because this production process are all the same, because we are considering only the standard model production process. Yeah. So here, let me briefly introduce why this complete this decomposition can happen. In order to do that, let me consider this kinematic configuration in the center of the string. Then if we set the kinematic configuration like this, then the corresponding this annihilation process amplitude can be between like this. Here, you can observe the lambda and sigma. Lambda and sigma are the helicities of the particle chi and y1 and y2. And this is the angular dependent part, and then usually which is called the Wigner D matrix element. And then here this is called the reduced amplitude corresponding to the annihilation part, and y is reduced amplitude corresponding to the production part. And then in this formalism, the identical particle relation is given like this. Here, the lambda 1, lambda 2 are commutative. So, and then this condition is coming from the angular momentum conservation, because the mediator spin is 1. So the helicity difference of the final state particle and initial state particle has to be smaller than 1. So by using this condition and this condition, we can reach a conclusion that the difference of lambda 1 and lambda 2 has to be +1 and -1, not 0. So taking the absolute scale of the amplitude, then we can completely decompose this annihilation corresponding parts from the production parts. So from when we take the numerical analysis, we can consider only the annihilation parts, because our bearing value is the spin of the this iron particle. So next, let me compare the difference between the hypercharge interaction and electromagnetic interaction. As Professor Scopper said, in the case of hypercharge interaction, the mediators are photon and also C boson. But if we consider electromagnetic case, there is only one mediator, which is photon. So here I draw the corresponding annihilation process cross-section. So y-axis is just nothing but cross-section, and x-axis is the collision energy of this annihilation process. Here, what I want to focus is only a red line. Red line is corresponding to the double boson pair production channel. And the dashed line is corresponding to electromagnetic interaction, and solid line corresponding to the hypercharge interaction. As you can see, the high energy behavior is more better in case of the hypercharge interaction. What is the region? The more high energy we go, then finally these two diagram is disconnected if we consider hypercharge interaction, because this Majorana current is coupled to the U1 gauge boson, but this W boson current coupled to the SU2 gauge boson. So we can expect that the disconnection, the higher energy we go. So we can say that considering the hypercharge interaction instead of electromagnetic interaction, we improve the unitarity properties more.
I know.
Yeah.
Yeah, how did you get, how did you set the curve at 10 TeV? Just you pick up 10 or?
Yeah, just I pick up 10 because since now the cutoff scale is very larger than the collision energy. Yeah, there's
So it's basically, the curve is unknown.
yeah unknown exactly yeah. Just I pick up physically. Yeah. So from now on, in order to focus on the numerical analysis, I'm going to fix the U1 gauge boson to be hypercharge gauge boson, which is given by the linear combination of photon and G bosons. The first constraint is coming from the Rayleigh abundance. In order to do the let me consider this annihilation process. Here, the corresponding cross-section is given by like this force spin 1/2 and 1. Here, beta chi is the annihilating dark matter high speed, and square root is the annihilation energy in the center mesh frame. So as you can see, both of case has the 1 power of speed, high speed beta chi. So for speed 1/2 case, we can say this process is p wave dominant process. On the other hand, for speed 1 case, there are two independent couplings. So at the first time, I'm going to consider only two cases, which is that only A1 coupling is alive and only B1 coupling is alive. So if I'm going to say each case as a A1 case and B1 case. So A1 case, there are additional beta chi to the 2. So because of the presence of beta chi to the 2, the A1 case is the D wave dominant process, but B1 case is P wave dominant process. So since A1 case is D wave dominant process, we can expect the stronger constraints compared to B1 case and or spin 1/2 case. So all the information that I have said up to now is fully included in this constraint plot. Here, the y-axis is a normalized coupling by cutoff, and then the y-axis is just a dark matter mass. As you can see, for spin 1/2 coupling and B1 case is much lower than A1 case, the Rayleigh abundance line. So here I filled out the gray color, and this region is fully excluded region, and then the white region is allowed region. And then maybe you can observe this overall factor. This is coming from the spin average of the annihilating iron particle. However, since now we are considering the scenario of the spin 2, we can observe the much more smaller the spin average factors. So since we can draw this black line according to this formula, we can expect that if we go to the higher spin scenario, we obtain more stronger constraints. So as you compare for the lower and higher spin case, you can observe that the higher spin case has a stronger constraint a little bit because of this spin average factor. The next experiment is the monojet, the monojet searches at the LHC. Here I drew the one of the most dominant process of the monojet process. The corresponding cross section is given like this. Here, as you can see, and also as I mentioned, because of the property of the Anapole vortex, what we can consider is only these production parts. The remaining parts are completely the same for all the spin cases. So please focus on the difference between spin 1 and 1 case. There is the distance. Distance is coming from the longitudinal component of the dark matter particle. By the way, here Q is the invariant mass of a virtual photon or virtual 지보전. And then because of the energy momentum conservation, the invariant mass Q of photon or 지보전 has to be larger than 2 times of dark matter particle mass. So this term is always larger than 1. So because of this, we can expect that the spin 1 case get the higher, much more stronger constraint as described in this constraint figure. In this case, this beta dependence is negligible because now we are considering LHC, the invariant mass of virtual boson, virtual photon and virtual 지보전 is very, very larger than dark matter mass. So beta chi is almost 1. So because of this region, as you can see, there is no big difference for A1 and B1 case. What about the higher spin case? If we go to the higher spin, then we can observe the numerous the longitudinal components. So because of that, the power of this term is getting higher the more we go to the higher spin case. So because of this term, the higher spin case suffer the stronger constraints more. So in order to comparison, I'm going to show you the lower spin and higher spin case. And the final experiments is the direct detection in the Jaehoon mapping experiments. Here, what I considered is this scattering process, and also as I mentioned in the property of the Anapole vortex, what we can consider is only this scattering part of the iron atom particle. So the property is fully included in this formula. Here, large ER is the liquid energy, and then now we are considering the GeV scale dark matter mass. The liquid energy is much smaller than dark matter mass. So this red color term is much smaller than 1. So at the first time, we can compare the A1 orbital coupling and A1 coupling because these two couplings include only constant dominant power. So as I mentioned like this, you can observe for the coupling A1 orbital and A1 case, there is no big differences. But in the case of B1 case, there is only this term. This term is which is very smaller than 1. So because of this fact, we can observe that the constraint for the B1 case is very weaker than the other case. Then how about the higher spin case? In this case, we also get the smaller spin average vectors, but because of the statistics, in the case of direct detection, the higher spin case get the weaker constraints compared to the lower spin scenario. As you can see, there is a very slight difference for the lower spin case and higher spin case. But as you can see, for the higher spin case, get the weaker constraints. So finally, let me combine all the constraints coming from the three experiments. And then, as I told you before, in order to take the numerical analysis, we additionally consider the naive EFT photovoltaic bound. So the bound is written by the formula for the bound is written like this. And here C is just given by the combination of couplings. And then the corresponding bound is drawn as an orange color. So first, let me consider only spin 1/n1 case. As you can see, for spin 1 case, totally get a stronger constraints because of LHC and then the Lellig abundance. And as you can see in the A1 case, there's no allowed lesion. But in the case of B1 case, there is still allowed lesion. And then for the spin 1/2 case, usually many people wanted to detect the spin 1/2 dark matter rather than the higher spin dark matter. But as you can see here, the dotted line is the future general experiments, and dotted red line is the general experiment with the 20 exposure, and then the dotted blue line is the high luminosity LHC sensitivity. So these future experiments can almost nearly half of can prove almost nearly half of the allowed lesion. So this is kind of a promising result for the future experiments. Then how about the higher spin case? As you saw, the LHC constraint get the very stronger constraint. So almost allowed lesion is fully excluded because of the LHC. And then if we consider the high luminosity sensitivity, we can almost fully exclude all these higher spin scenario. Then, as mentioned by Professor Scopper at the first time, how can we deal with allowed lesion when couplings A and B both alive? This was a main question to us when we write down the paper. In order to investigate such a case, which both couplings are alive, we needed to fix the document mass. And then for the convenience, we also fixed the cutoff scale value. Then, because of the cross-section form, which is given by the combination of A scale and B scale, this is also applied to the spin 2 case. All the constraints will given by the ellipse. Of course, this red line is also ellipse, but this is nothing but the vertical axis is very long. So this looks like just a vertical axis. So as you can see here, the blue line is the constraint from the LHC. For the spin 2 case, this constraint is very much shrink. And so finally, all the allowed lesion is fully excluded.
So what is the allowed region? The white?
The white one.
The white one.
Yeah.
So you still have the small part.
Yeah, exactly. Yeah, even though we consider spin 2 case, there is a very, very tiny allowed region. Maybe it is hard to see the allowed region. Yeah, there is a very, very tiny white region. Yeah, so in order to see that, we choose the mask just to show the allowed region. This is the reason why we took the mass value as a 1.25 TB.
So what I don't understand is if you're summing the absolute values,
Sorry.
if you are summing the absolute values of A1 and B1, the bound that you get for the combined A1 and B1 should be stronger than the bound separately for A1 and B1.
Yeah, this is just depending on the dominance of coupling.
Yeah, well, no, what I mean is that you say, okay, if I consider separately A1 or B1, I find some regions. Then you say, okay, I combine the two. You can find additional. So you can always find a stronger bound if you combine it. Because you are summing, you cannot have negative interference between the two. You understand?
Negative interference about this.
So suppose that a certain value of A1 alone is excluded.
Yeah, A1 is excluded.
Okay, a certain value. Now you say, okay, I have also B1. It's still excluded.
In this case, if we choose the A2 value, then the point is here. Yeah, because a B2 value is 0. So in this case, you can say A2 value is completely excluded for even though we choose any value of A2. But in the case of B2 case, then A2 has to be 0. Yeah, so in this case,
B2 is larger.
yeah, this is.
But this is possible if you can have a negative interference, so the signal goes down.
There's no interference
Yeah,
between
exactly.
A1
This is what I'm just wondering, how can you recover a value that is excluded for B equal to 0, for B different from 0, if the signal can only grow, can only increase? You understand what I mean?
It's probably the Rayleigh region is going down because of the cross section.
The Rayleigh abundance, yeah, exactly. So the annihilation cross section in the Rayleigh abundance
Going up.
is going up. Okay, so yeah, because the signal in LHC can only increase.
Yeah.
Okay.
Yeah, the Rayleigh abundance is getting powerful and LHC is getting powerful and only Zenonanty is getting weaker.
No,
Yeah.
I think that, so all the cross sections are getting higher because if there is no interference, you're just summing more contributions.
Let me go.
That's the, why it was not done.
Let me go back to the Zenonanty scattering rate. Here, as you can see, because of the spin average factor, the cross section get the smaller value for the higher spin case.
No, I'm not comparing different spins. I'm comparing a case where you have only A
Yeah.
with a case where you have A and B.
Yeah, A and B.
And of course, all the signals go up, all the cross sections go up. They can never go down because there is no interference. However, the Rayleigh abundance, the annihilation cross section is going in the other direction. Now I understand.
I see. Yeah, finally, conclusion. Yeah, I in our work, we took the general analytic and numerical analysis of the hypercharge Anapole barometer for spin 1/2 to spin 2 cases respectively. And then I introduced the construction of the general Anapole vortex. And then I mentioned for spin 1/2 case, the future experiment is very promising. Because as you can see, almost half of the allowed region can be excluded. And then also for the spin 1 case, the high luminosity LHC can prove or about nearly half of the allowed regions. And then summarizing the tendency of the construction and of the constraints from each experiment is given like this. In the case of rally, we get a stronger case. For the higher speed cases, LHC also get a much stronger constraint, but general empty case, the weaker constraints for the higher speed cases. By the way, as I mentioned at the early stage, if we consider the speed scenario larger than 2, then we must consider composite particle scenario because there is no nuclear complete theory up to now. So, but of course, if the composite scale is very larger than the energy scale now we are considering, then we can continue our continue and apply our methodology to the higher speed case also. And then also, since there are several allowed regions, we can consider the identification of the Anapole documental particle spin or another properties in the electron colliders. And also, as I told you before, since there are several allowed regions, we can also consider the UV scenarios of the hypercharge and Anapole particle. That's all. Thank you. Yeah.
Nice talks. Is there any question?
Yeah, please.
So this Euro region is, you mentioned, perturbative. This Euro region that you were excluding.
Yellow. Yeah, yellow region. Yeah.
Is due to what? It's perturbative.
Yeah, naive perturbative bound. So it is difficult to believe this bound. Actually.
Why this depends on mass.
I can go to this.
Yeah. This one, right? Yeah. Well, your question is why it is depends on mass.
Because S is 4 and square.
Yeah. This is just nothing but the collision energy scale. And then this collision energy has to be larger than 4 times the M2. Yeah. Since when we introduce this perturbative bound, I feel very bad. And then it is since it is difficult to believe this bound is real. So, but in such a point of view, actually, we cannot believe all the constraints.
What happens if you remove the perturbativity? Perturbativity is just lower magnitude, let's say.
Yeah, if we remove the perturbative bound,
Very high mass is still possible.
yeah. The higher spin, higher mass scenarios are still possible. Yeah.
So, what about spin 0?
Okay. Let me explain. The spin 0.
Okay, the other question is, you have all cross sections which are velocity suppressed. So that's why you have the annihilation cross section is P wave, D wave, and so on. So no hope to have indirect detection. Right? Indirect detection.
Yeah.
The annihilation of WIMPs in our galaxy and so on.
Yes.
So I'm just that's why I'm asking, because in the case of, so I guess that if you increase the spin, also the velocity suppression is going up.
I don't think so, because as I showed before, there's only P wave dominant and D wave dominant process. Yeah, only.
Which is, if you look at the diagram, the annihilation diagram. Usually when you have P wave, this is due to the fact that in the case of spin 1/2, for instance, when you have 2 particles of spin 1/2 in the limit the non-relativistic limit have parity -1. So when you have a propagator that has a parity +1, then you need also orbital angular momentum
Exactly.
to conserve spin. And in
Yeah.
this case, also Z and gamma has spin -1. So it's not that. You cannot understand from that point of view. So I'm just wondering if there is a physical reason to understand why this annihilation cross-section is suppressed when the orbital angular momentum of the two wings is 0.
I think your question is related to why there is no spin zero anapole.
No. It's why you always find
Velocity
P wave
yeah.
or P wave or D wave annihilation cross-section.
Yeah, that's the reason why, as you told me exactly, this is related to the parity violating parity even term. This
Where
is
is the parity even? Because okay, I don't know in the case of spin 1 or spin 1, but in spin 1/2, if you have two Majorana particles in the limit of spin 1/2, in the limit, non-relativistic limit, the parity is -1.
parity is
-1. And also gamma is parity -1, so I don't see any violation. So there has to be some other reason. So of course, I believe, but I'm just wondering if there is an explanation.
As far as I understand, the reason of the presence of the velocity suppression is because of the parity violation. Because if there is an orbital angular momentum, then the orbital angular momentum means the changes the parity. So the parity mode property is directly related to the velocity suppression. Yeah, what I understand is that's what.
Yes.
Mm.
Wait a moment. Can you go back to the original? No, I understand. To the original. Yeah, here. I don't know. Yeah, there is a gamma. In the case of 1/2, because there is a gamma file.
Yeah.
But in the other cases, it's not. We don't understand how it's doing.
Yes.
So it's just parity.
Yeah. But in the case of half displays, there's still gamma 5. Yeah.
Okay.
Yeah.
Okay, so spin 0.
Yeah. Actually, maybe the number of Majorana particles is not conserved. Right. Yeah. This is the reason, and we can observe such a phenomenon in the cosmology study. Yeah. Because when we calculating the number density of photons, the photon number density is not conserved. The total number is not conserved because the photon is the self-conjugated particle. So, of course, when we write down this paper, I got the question why there's no spin zero Anapole dark matter. So I tried to understand why there's no spin zero dark matter. Anapole dark matter. This is actually, if we consider the particle conservation in the Lagrangian level, then we must, if we impose the particle and antiparticle number conservation, then we need to write down the conserved current. Yeah, conserved current. But in the case of Majorana particle, as I told you, the number is not conserved. Yeah, but in the case of spin zero case, what we can write down is only conserved current. Yeah, that's all. The conserved current is it's maybe all of you know. Yeah, that's the reason. That is the reason why there is a gamma mu and gamma phi. If we write down only gamma mu,
Yeah, no, I understand.
yeah.
You need an index, mu, and this index mu will be derived from that current, but that current from my own part is 0.
Yeah.
Okay.
Yeah, by the way,
That's really good.
yeah, because of the number conservation. Yeah, but Of course, this vortex has another conserving quantity if we consider helicity. Yeah, that's the actually this operator in the non-relativity limit is exactly corresponding to the helicity operator. Yeah.
Which one?
That's gamma mu and gamma phi. If you be gamma mu and gamma.
Yes.
Yeah. So yeah, that's the reason why there is no spin zero anapole dark matter.
Because you need a receipt.
Yeah, it doesn't have a helicity. Yeah.
Is there any questions?
I'm very simple.
Yeah, please.
More document. What is the contribution?
Sorry.
To describe the document.
Yeah.
It's a contribution from your. So,
What is the contribution?
yeah, you, is there any new contribution to this?
Yeah, just as I told you in motivation, now we are not specifying a specific model. We are not specified any specific model, but what we consider is only that the dark matter interact with the U1 gauge motion. Yeah, so it is quite general scenario. So and then also in referee comment, from referee comment we get since considering the higher spin scenario of the dark matter is a kind of brand new research. Yeah. Referee told us like that. Yeah, I didn't say like that. Yeah. So nowadays, as I told you, many people consider and then they limited themselves up to only spin one. Yeah, but just according to our spirit, as I told you before, since now we have a very few information of dark matter, so there is no reason to be limited up to only one or only spin one dark matter. So maybe since we are considering the relativistic higher spin dark matter scenario, we are considering such a scenario. So there are I hope there are many fields where our mechanism or formalism can be applied to the dark matter physics. Yeah.
So it's possible to use the Anapole because of the classical electromagnetic interaction.
Yes.
So in the sense that you comment or people this is
But
the particle.
no, I think that what is interesting in this analysis is that, as he said from the very beginning, you are only assumed the two basic assumptions. One is that the particle is Majorana.
Yeah.
And the other is that you don't want to extend the gauge group of the standard model.
Yeah.
Okay. And then you think, what is the most general Majorana particle that couples to the group of the standard model?
Oh my God.
Is a Majorana particle with arbitrary spin, and the only coupling which is possible is Anapole. And what he has shown is that basically it's almost a spin. I don't know what's going on.
He knows more than me. Oh my God. Yeah, this is our most important
Yeah,
motivation.
this is very simple. It's like how do you say? Razors, Occam's razor. So you just want the minimal assumption. I don't
Yeah.
change the group. The interactions are exactly the same. We remain the same. The only thing that I allow is only Majorana, because if he has Dirac, then we can have also magnetic dipole and electric dipole, and then it's not longer true. He has some parameter space. But if you just, for some reason, you want to believe that the dark matter particle is a Majorana particle, and you want to have the minimum interaction possible, that's the situation, basically.
Yeah, that's all. Yeah, that's your whole system. Yeah.
I have a question.
Yeah.
Do you have any guess about what the UV complete theory of this model could be?
Of course, we already listed the UV complete purely,
Ah.
because if we don't do that, all the referees never accept our paper.
It's not true. Why? Because we have no idea what the new physics is.
Yeah.
Uh,
Yeah, but
but
several,
you have some model.
yeah, of course, for spin 1 over 2, we can consider the win. No, sorry, the Vino and Vino. Like
Some specific parameter space of supersymmetry.
Yeah.
So you are considering like supersymmetric model?
Yeah, just if someone want to mention about the corresponding UV complete scenario, then we can say for spin 1 over 2, there's a sushi, and for spin 1 case, there's a Color-Klein excitation of photon and G-boson, yeah, something like that. And then spin 3 over 2 is a graviton, and then spin 2 is a Color-Klein graviton. Yeah, we can make a lot of not a lot of several complete scenario. Yeah.
I have one more.
Yeah, please.
To describe the document.
Yeah.
This is the maps of quantum mechanics. Some should have some static property of the density profile and spatial.
In this case, we just follow the trivial thermal freeze out scenario. Yeah, so we didn't consider such a details. Yeah.
So if you have other questions, we can discuss it later. So that's thank
Thank you so much. And finally, since Professor Scopel pointed out my most important motivation, I was a little bit jealous to him.
He repeated what you said. Right?